The Wiggers diagram is a comprehensive graphical representation of the cardiac cycle, illustrating the dynamic changes in pressure, volume, and electrical activity within the heart over time. It integrates key physiological parameters including atrial, ventricular, and aortic pressure, ventricular blood volume, and electrocardiographic ECG activity to provide a detailed understanding of cardiac function. I should point out that for this video we will be focusing on the left side of the heart, but do note that the concept is exactly the same on the right side. During most of ventricular diastole, the atria will also be in diastole, which can be seen as the TP segment in the EKG, the period after ventricular repolarization and before another atrial depolarization. During this period, the AV valves will remain open and the ventricular volume will steadily increase. As the ventricles continue to fill during late ventricular diastole, the SA node will reach its threshold and fire an action potential that will spread throughout the atria. This electrical discharge can be visualized in the EKG as the P wave. Atrial depolarization will then lead to atrial contraction, which will cause a small bump in atrial pressure as the blood volume within the atria is evicted into the ventricle. The increase of ventricular pressure that mirrors atrial pressure is a result of the blood that is expelled from the atria into the ventricle post-atrial contraction. Throughout atrial contraction, the AV valves remain open due to the higher pressure in the atrium. Once atrium contraction ends, ventricular filling also ends and the end diastolic volume is reached. This marks the end of ventricular diastole and the onset of ventricular systole. After atrial excitation, the electrical impulse will travel through internodal fibers to AV nodes, passed through the bundle of His into the bundle branches, and is finally distributed throughout the Purkinje fibers to stimulate the ventricles. All of this happens as the atria continue to contract, and by the time ventricular activation has been completed, atrial contraction has also finalized. This electrical impulse that travels through the heart's conduction system, culminating in ventricular excitation, is represented by the QRS complex. Shortly after excitation-contraction coupling has occurred, ventricular pressure increases due to the onset of ventricular contraction. Due to the now flipped pressure differential between ventricles and atria, the AV valves will close. During isovolumetric contraction, the ventricles contract with all valves closed. This causes pressure to rise within the ventricles with no net volume change until ventricular pressure exceeds the pressure in the aorta. Only then do the semilunar valves open, allowing blood to flow out. Aortic pressure continues to rise and ventricular volume drops as blood from the ventricle rushes through the aorta. It should be noted that ventricular systole includes both isovolumetric contraction and ventricular ejection. It should also be noted that the ventricles are never fully emptied. Only a bit over half of the end diastolic volume is ever expelled, and the remaining blood volume is called the end systolic volume. The difference between the end diastolic volume and end systolic volume is the stroke volume, the amount of blood that the ventricle ejects during contraction. The T wave here signifies ventricular repolarization at the end of ventricular systole. As the ventricle begins to relax, the pressure within the ventricle begins to fall, and once ventricular pressure is lower than aortic pressure, the semilunar valves will once again close. The closing of the semilunar valve will cause mild turbulence seen as the dicrotic notch. During this period, the AV valves will remain closed since the pressure in the ventricles still exceeds atrial pressure. This period is called isovolumetric ventricular relaxation, a period where muscle fibers relax and lengthen, making pressure fall, but volume will remain constant. Once ventricular pressure falls below atrial pressure, the AV valve will open and ventricular filling will onset once again. Ventricular diastole includes both isovolumetric relaxation and ventricular filling. Atrial repolarization occurs at the same time as ventricular depolarization, meaning atrial diastole occurs throughout ventricular systole. Blood will continue to flow through the pulmonary veins into the atrium, which will cause the pressure to rise. Once the AV valve opens again, the pool in the atria will rapidly fill the ventricles initially, but will taper off as pressure between the chambers equalize. During late ventricular diastole, the slow filling period, the SA node fires again and the cycle begins anew, repeating the sequence of events with each heartbeat.